Um, First, I would like to welcome you to this one-day workshop, which will talk about dynamic solutions and how it can affect oil and gas production modeling and optimization and troubleshooting. This is one of the more recent topics in oil and gas industry, how we can utilize transient or dynamic simulators to produce a more reliable and more of accurate representation of our production systems. So before we start, it's important to get to know the presenter. My name is Nashat Umar. I have more than 9 years experience in oil and gas industry. I am an experienced production engineer, as well as I work in dynamic well modeling and flow assurance as well. I worked in many companies. For example, I worked for Schlumberger as a production engineer, and I have filled many roles. For example, I worked for like 2 years in drilling engineering, and as well as I was working in production data management systems using Avocet software. So on our agenda, what we have, we will take a look at the basics of production systems and what that is composed of, and the production data acquisition and monitoring process, the classical modeling of production systems, limitations of system analysis or known as nodal analysis, and from this slide and on, we will talk about dynamic solutions, which is like more advanced solutions of production system modeling and how it can affect the accuracy of our representation. We'll talk about as well how to represent reservoir in these solutions. We'll take some applications like real-time cases, or sorry, real field cases in these types of simulators. And the last two topics, we'll talk about how we can leverage these kinds of solutions to produce some results as a surveillance tool, for example, like real-time calculation, and how to manage these types of models using programming. So let's start with the basics of production system. All petroleum engineers know what a production system is. A production system is any system can produce hydrocarbons along with some non-hydrocarbon fluids, for example, water. A production system is composed of many parts. So it's the main core, and the main part of the system is the reservoir. And then to start producing from the reservoir, we need a well. A well is a hole drilled in the reservoir or in underground to deliver the fluids from the bottom hole to the surface. We have the surface connections, and we have the production facilities. The surface connection actually connect the wells to the production facilities, and then the facilities itself is connected to the storage facilities. So this is the basics of what a production system is composed of. So if we take a look at what types of data we're acquiring from the production system, at least from my point of view, I can divide production system data acquisition into three categories. The first category is the daily acquired data. So daily data is the operational data that we get from oil wells and production separators and equipment. These can be, for example, wellhead pressure, wellhead temperature, oil rates, gas, water rate, equipment temperature, equipment pressure, delta pressure across the equipment, for example, orifice plates. So all of these data, actually, we are getting them as daily data. However, some newer digital oil fields, they are utilizing more robust acquisition system, and they are getting the data minute on minute basis and sometimes even second basis. The second category of the data is the monthly data, which is like an aggregation of the daily data. In addition to all the data we have in the daily category, we get them in the monthly. However, they are aggregated and they are filtered for the noise and they are mostly averaged. What the benefits we can get from the data is to know what wells we're producing for a specific month and how many hours a well spent on the stream and the stability and the instabilities that a well was experiencing. For example, not always the stability or instability is shown in the daily data. However, if the data is plotted on the monthly basis, it can be shown very uh, pronouncedly. And the last category of the data is the sporadic data. These data actually, they are known sometimes as event-based data. So these are sometimes scheduled on and sometimes unscheduled. For example, if we take a pressure survey of the reservoir, this is known as sporadic data. Sometimes we schedule these types of surveys, and sometimes we don't schedule them and just conduct the job based on the needs of the reservoir or subsurface team. Other types of the same category include the PLT, production logging tool, static grading observation, dynamic grading observation, and so on and so forth. So this category of data acquisition is basically usually based on event basis or jobs that conducted on the field. So to take a look at what this data could look like on the data acquisition. From daily data, actually, we usually get tubing head pressure. We get casing head pressure, and we always get flow rates for nearly all the phases. The main issue with the daily data we get is there is no place to put them inside production modeling softwares. The production modeling software only takes a single value, and that makes a problem for us because when you are getting daily data, you're for a single month you will get like 30 data points, and at the end of the month when you're trying to do some modeling, so which value you will put inside the model. So there's some data science in the selection of that value. This goes for like all the operational data. And the most important question is, am I getting like the full benefits from recording all these data on a daily basis? Well, in the current solutions we are having for petroleum, for production engineering, the answer is no. Mostly reservoir engineering guys are making use of these daily data, but the scene is changing, and in the upcoming slides, we will see how to leverage this type of daily data and to how to incorporate them in inside a modeling and simulation software. So we'll start to talk about, from now on, we'll start talking about how to do some production modeling and how production modeling process works. So the first thing we will take a look at is the classical production modeling. So classical production modeling, this is known as a nodal analysis or system analysis. However, it all started in 1954 when a guy named W. Gilbert, which he published a paper. He was talking about how he was modeling gas lifted wells and natural flowing wells. So this is actually a very interesting paper because in that year or in that period of time, there was nothing called such as system analysis or nodal analysis. He was, to my knowledge, he was the first person who introduced this concept. However, he does not explicitly say it in his paper, the name of the method he's using. No, he was talking about well performance evaluation. He did not give it a name. So these two photos actually, I snipped it from the paper itself. Gilbert's paper is very pivotal in production engineering because he introduces three main concepts. The first concept is he introduced the combination of inflow and outflow performance on the same plot. The second concept is he introduced it at equation to evaluate multi-phase flow at the chocks. And the third thing is he he introduced as well something he called curved IPR. This is like 14 years before Vogel even he started his work on IPR for solution gas drives. So this paper is actually is very important for production engineers. This is the reference for the paper. If you like to, for your references, if you like to take a look at the paper can be found on One Petro website. So derived from that paper, the current classical production system modeling is known as nodal analysis. The approach actually is used to optimize and design, optimize, and evaluate a new production system or existing production systems. So this type of method actually provides two main outputs for us, which is the Q and the P at any given operating point. So the main plot we are getting from this is the nodal analysis plot. This is the plot where the nodal analysis plot is composed of two components or two main components. The first component is the inflow performance relationship, and the second component is the pressure traverse equation. And how did we get there? Actually, we will get there by dividing the production system into two main components. For example, if we have a production system like this is a well, and this is our reservoir, denoted as R, and this is our well, and this is our surface facilities, surface connections. So if we divide the reservoir or the production system from this point on and added a node here, so this is known as nodal analysis. The fluid where is flowing from the reservoir to the bottom hole, this is known as the inflow. And there is a set of equation or set of correlation to represent this flow or this phenomena. And the fluid that's flowing out from the reservoir, from the bottom hole to the surface, this is known as the outflow. So by combining these two equations, it's evident that there is only a unique pressure and flow rate that satisfies those both equations, and thus the intersection happens in this point. So this intersection is very infamous for petroleum engineers. This is known as the operating point. If there is no intersection at all, this is known as the system is not intersecting, or there is no converging solution for it, meaning that the system is not producing. So this is basically the classical approach for system analysis. And the softwares that can do this job is, for example, you have PipeSim, Prosper, and another software called WellFlow by Weatherford. However, we have few issues with these types of softwares. You can think of these type of software as legacy softwares, or let's say a legacy method in modeling production systems, because they impose some serious limitations, because those limitations are not inherited from the software. No, they are inherited from the methodology that was adopted while creating the software. We will take 3 examples of these serious limitations of this type of software actually impose on the procedure itself. The first thing is there is no explicit relation to time. For example, if you take a look at this plot, which is known as a nodal plot, you will see there is no time mentioned in this, meaning that while running the simulation, when you get this result is valid only for the data you input. For example, if you have a well test you did for like 3 months ago, and you have data close to that time and date, if you create a model now using that data, this means that the model created now actually represents the time of that previous 3 months ago. So this is some serious limitation we need to think of. There is no relation to time. So if I want to create a model while using all data, however, I want to predict its performance now and how the performance degrades over time, this is actually, it's not possible using use any of the softwares currently available in the market. But what you can do, you can assume any numbers of pressure or any numbers of flow rate you want. However, this is not accurate, and you don't know actually how the pressure is changing with time. So let's take a look at these two equations. The red equation, denoted as A, this is the inflow performance. The inflow performance in this equation is linear. However, it's shown as curved in the plot. This PI term is known as Darcy term. This is coming from the Darcy equation, and it only contains the rock properties and the fluid property itself. We have the flow rate and we have the delta pressure, which is known as the drawdown. So we are sure that the units of the pressure is PSI gauge or any other units you are using. And the liquid contains the unit stock tank barrel per day. So this is the only time where the time factor occurs. However, this flow rate only represents the time of the well test. And if we take a look to the second equation, which is known as the pressure traverse equation or the mechanical energy equation, we see the time term only implicitly occurs in the velocity term. So meaning that the velocity is actually the fluid velocity during the well test or during the values we took for the well. So all of these terms, actually, they are not related to time. For example, density is not related to time. Friction factor is not related to time. Gravity, conversion factors, diameter, length, these are all not related to time. So we have, there is a solution to link this system model to time is by using material balance in conjunction with the classical nodal analysis. So the second limitation in classical production modeling is the representation of the reservoir. So if you take a look at the equation that's presented on the right-hand side, you can see it's the productivity index equation. And it's just too simple. So do you think that this equation actually represents the reservoir itself with its complexity and its heterogeneous and the fluid distribution? The answer is simply no. This actually does not represent the reservoir at all. However, we use it for the sake of simplicity. So most IPR models are single point models, meaning that it represents the reservoir as a single point, and the result is aggregated in that term, and we can use them in our production system modeling. Usually these equations are empirical, and they are derived from empirical data, from field data. Additionally, there is another thing that's inherited in the IPR. It does not account any change that's happening in the reservoir. And this is, again, this is related to the no presence of time in this type of representation. So this is so we have two equations here, equation number 1 and equation number 2. Equation number 1 is the productivity index, and equation number 2 is the Vogel method of inflow performance. If we take a look at the Vogel equation, we see there are a few numbers of interest. For example, this 0.2, 0.8, and productivity index as well. And we have this square. Okay, so those are all empirical values. So this meaning that you can change them. However, the degree of the empiricality of these values actually will change the behavior of the equation or the result all the time. For example, newer research show that manipulation these two data using Vogel's method actually change the behavior of the IPR and will give you the capability to fit the IPR for other types of reservoir, for example, heavy oil reservoir. These types of paper actually usually actually there are two types of there are two papers that's talking about changing these two numbers to fit them to the field data, and both of them are written on the Venezuelan oil, which is usually heavier than the water. So as a solution to this simple oversimplification of the reservoir, we can do two things. The first thing is to link material balance to the reservoir, to the well model, okay? And the second thing, which is the most appropriate thing, is to create a numerical simulator or create a numerical earth model and connect that to the production system. And the second one is much more accurate and gives us a good grasp of what's happening downhole. So let's go to the third and the final limitation we're talking about is the complex phenomena that happening inside a well. So what do we mean about complex phenomena? For example, whenever we are producing, there are complicated things that's happening inside the well. For example, the liquid loading, fluctuation in pressure, the presence of slug, deposition that's happening inside the well. These are just for an example. And unfortunately, classical production modeling softwares like Pipes and Prosper, they can't do this prediction because simply they are steady state models. Additionally, if you want to predict these, actually you have to look elsewhere because these types of software will not do the judgment for you to assess if your well is experiencing instabilities or some complex phenomena. One more limitation is the limitation we talked about while data acquisition slide. These types of models only take single value as operational value. For example, if you are inputting wellhead value, you will have to input it as a single value. So you have to do some data science in that area. For example, you can use the mean or the mod or do anything that to extract a single value from a set of values. And this is as well inputting the values as array or as a list or table. It's not possible in the classical production system approach. But all that was going to change in the 1980s. So a team of scientists who were working in IFE and Scientific in Norway, they all participated in working on a project that was going to change the production scene in oil and gas industry. So in the 1980s, the first of kind of a dynamic simulation was introduced in oil and gas industry, which is known as Olga. These four people, actually, they were one of the pioneers who worked on the project. Olga was intentionally made to predict the flow in pipelines and other flow components as well, for example, valve, etc. But since the 80s up to now, Olga been used in a lot of projects, and it's even used in horizontal wells, smart wells, vertical wells, and to capture all the complex phenomena that the classical production system did not simply provide. There is an interesting paper of how Olga works, and it's one of the only papers that describes the internals of this simulator. The paper is provided by SPE. This is the number of the paper, and you can search it and download the paper. So it talks how the Olga was made, the history of Olga, and how they are benefited from the reactors that worked on a similar code. So it's a very interesting paper. However, I would like to warn you, the paper is old. It's more than 30 years old. So a lot of things have changed in that paper. However, it's good to know the basics. So let's take a look at what types of issues softwares like Olga can do for us. By the way, Olga is officially known as dynamic multi-phase flow simulator or transient multi-phase flow simulator. So what we can do with Olga or any similar software to Olga like LidaFlow, we can do well shut-ins and well startups. This is one of the areas I tried Olga uh, quite often, and it's every time it succeeds. By the way, the well shutting and startup is one of the complex phenomena that's happening inside the well. And unfortunately, most of the time, the wells that we shut in, they do not start up normally. We need to inject some form of nitrogen or any form of gas in it, so to light up the columns of the fluid, so we can initiate the production from it. We can use Olga as well, or dynamic simulators for bean size optimization. We can use them for production system ramp up. Quite often when you have a production facility, for example, let's say we have a production facility that's its rated capacity is 25K of barrels, and you want to crank up the bean size on, let's say, a couple of wells. So in order to increase the production, it's not just as simple as like adding one plus one equals two. No, there is usually instabilities related to the ramp ups or the cranking of the production. And these type of instabilities, they are easily detected with Olga and can be used to schedule or design the proper ramp up for our system. Additionally, Olga is used for naturally flowing wells, as well as wells that have ESP and gas lifts with it. So the classical production systems, softwares like, for example, Prosper and Pipesym, they can do designs of ESP and gas lifts. That's given, and they are do it very well. However, what they fail to do is the determination of the stability of these types of design with the change of time and the change of operational parameters. So they don't do that. However, in the newer versions of Pipesym, there's a stability map included with the Pipesym software that it solves some of that issue, not all of it. It's known as Al-Hanati stability map. It's a stability map that's used with gas lift operations, so you can have a look at the operational parameters and how they affect the stability of the gas lift operations. Additionally, the dynamic simulators can be used to detect liquid loading. Liquid loading is the process of liquid accumulation in the bottom hole. Usually, this is presented in gas wells or gas condensate wells where there is no proper velocity in the gas to carry up the fluid to the surface. So the liquid will start loading up inside the well, and the well will get cease production sooner or later. So this usually requires some form of intervention method, for example, like pumping or soap sticks, or sometimes in the severe cases, you need to bring up the cold tubing unit and just suck the fluid or just circulate the fluid. So there is some cost associated in this area. Okay. So we can easily use Olga to detect when we'll have liquid loading and how to create some mitigation strategy beforehand. One of the cool things you can use softwares like Olga or dynamic simulators in is the well cleanups. So most companies, like we're talking about, like small scale companies, they do not have access to softwares like Olga. So how will they clean up the well after drilling or after workover is there are three main methods. You have either you can use a silk line with some suction cup to suck up the fluids and lift some of the hydrostatic pressure and maybe initiate some production. And by the way, this method is somewhat banned in the bigger companies because there is some serious HSE related issues with that. Other methods are just circulating diesel fluid, which is a low density fuel. It lights up the well, and sometimes the well does not even start to produce. And the final thing that people then operational people do is to inject nitrogen, or it's known as N2 circulation or N2 lift. The main reason we can use Olga for this thing is to plan the cleaning process. For example, if we are about to drill a well, or we are about to work over on a well, what we can do is create a model for that well and add all the completion fluids inside the model and try different strategies. So we can try the strategy of diesel circulation. If that does not work, we can try nitrogen circulation until we get a satisfactory result with optimized parameters. For example, if you need to circulate nitrogen for only 4 hours, so why you're keeping the unit for 24 hours or 12 hours? So these parameters, they are usually optimized through softwares like Olga, which they are dynamic simulators. Only Olga and similar category software can do these types of jobs for us. One of the important things we can do as well in Olga software is the integration between reservoir and production. So this means we don't need anymore to rely on IPR. No, now we can use numerical reservoir models. So this actually, this type of coupling or this type of integration actually helps us on capturing all the complex phenomenon that is happening inside the well and the near the well inside the reservoir. Additionally, there is a very nice and nifty use of Olga software or any dynamic simulator is the detection of the cross flow that's happening. So a lot of times when we have multiple layers producing in the same well during shutting or during the production itself, there is a cross flow between those layers. Of course, the cross flow or the flowing fluid is going to flow from the high pressure to the low pressure, and you will get some production loss in that area. Usually in the field, this is detected using PLT package. However, you can use Olga to detect that phenomena as well and count how many how many barrels of fluid you're using or you're losing to a set of to any given formation. This is not a comprehensive list of Olga uses. There is a paper on SP which is published in 2007. The paper is like 20-page long or something similar to this. The paper is called the Virtual Well Guidelines for Application of Dynamic Simulation. This paper actually, it's very good paper. It shows you all the use cases, or sorry, let me rephrase, all the possible use cases of Olga software. And just a notification, this paper was published like 15 years ago. So there's some usages have been added inside Olga. So you might not find it in the paper. However, the paper is a very good paper. I read it multiple times. It provides you a good insight of what Olga dynamic simulators can do for you. The next topic we will talk about is how advancement these types of simulators have replaced the reservoir representation from IPR to numerical simulators. So inside Olga or any given simulator, you can use two main methodologies to represent the reservoir. The first methodology is the reservoir simulator. The first method, actually, it's somewhat similar to the method used in PipeSim and Prosper. However, there is a twist. All the parameters inside the equation of productivity index or the Vogel's equation, they can change with time. And this is the main difference with Olga. For example, if we take a look at the inflow performance, the productivity index equation, which PI equals to Q over delta P. Okay, so inside Olga, what you can do is create a function of Q and change it with time. So whenever the simulation goes on, it will change the Q value and calculates new PI. And you can do the same for the delta P as well. Or you can do that for only for the reservoir pressure and just provide a function of how the reservoir pressure is changing with time. This will be very helpful for you. It produces a much more accurate representation of the reservoir. If you don't want to do that, what you can do is use numerical reservoir simulation. Now, softwares like Olga come with a numerical simulator known as ROX. ROX is a smaller representation of Eclipse 100 code. And Schlumberger people have created a small numerical simulation software that can go along with Olga. What you can do is create a numerical model and link that model to the Olga software. And this can be used to model various geometries. For example, you can use it to model vertical, directional, and horizontal wells. There are two main types of grids you can use in numerical simulators regarding Olga. You can use radial representation or radial gridding or Cartesian gridding. So the selection of it, it depends upon the user preference. So we will from now on we will take real case examples inside Olga. So please, if you have any questions regarding the slide presented so far, please feel free to ask before we dive in much more deeper inside Olga software. So if anyone has a question, please feel free to ask before we dive deep in the Olga simulation. So I assume there is no questions. So in this workshop, we will talk about 3 cases. These are just an example cases from data or the projects I worked on, and some other cases that it just comes with Olga. So the first case is how to use Olga in well shutting and startup. The second case is how to clean up the well using Olga. And the third case is how crossflow is detected inside Olga. So let's dive in with the first case. So whenever the well is being shut in, that means there is some valves being closed inside the well or on the surface that prevents the fluid from flowing from the bottom hole to the surface. This is known as the shut-in. And a shut-in state is a state of the well where there is no production is coming out of the well. The shut-in is usually intentionally made by the field personnel to do due to some operational consideration. Let's take an examples. Why do we need to shut in well? For example, when we are monitoring gradient stations or we are doing a slickline job, we need to shut in the well. And sometimes we don't need to shut in the well. However, some jobs requires the well to be shut in. If you are trying to monitor gradient station or static gradient stations. If you are trying to do some pressure surveys, some reservoir pressure surveys, you need to shut in the well. Sometimes field personnel intentionally close the production from the well or suspend the production for well to allow for the reservoir pressure to recharge. This is known as stop cocking. This is usually done in the later life of the wells when you have like a depleted reservoir or something similar to this. And shutting in the well usually can be used for water coning control. All of these uses are required a well shut-in. However, there is a catch. What if you shut in the well and the well did not start again? So let's just that sink for a moment. So do you think the startup, there is a huge uncertainty? Does the well start again or it does not? And if it starts again, does the startup is going to be stable enough for it to continue production for the upcoming days, or it's going to be uh, accompanied with instabilities and the well is going to die in the upcoming days? Many field cases and field scenarios actually suggest that once the well starts again, this is we're talking about like wells. They usually they are completed on the depleted reservoirs or something. Most of the time, the wells can start. However, they fail to maintain production, so the well dies in the upcoming days. What we can do is we can predict all that scenarios and just eliminate the inconveniences, the occurrences of these types of events. So, what are the governing issues in the well shutting and startup modeling inside Olga? First of all, you have the phase segregation inside the wellbore. This is one of the main governing issues. For example, if you have a flowing well in this plot A here, the fluids usually is mixed and they are produced, all the phases are produced at the same time. However, whenever there is a shut-in, you will find a clear or a distinct separation between all the phases. So this is known as the phase segregation. So the the most important question to ask is, what is the height of the water inside the well whenever I shut in the well? What's the height of the oil column, and what's the height of the gas column, and how high the pressure on the wellhead is going to be when I shut the well? All of these questions can be answered in two ways. First of all, whenever I shut in the well, I can do some select line job and just run in whole some memory gauge or any pressure gauge to be precise, and we can measure the gradients, and from the gradients we can calculate the slope for each phase, and we can know the contacts. However, this is costly. What we can do is when we create Olga model and we shut the model, the Olga model shows us whatever we have contacts between the phases. The second governing issue is how long is the water column. All oil field personnel knows that the more the water, the worse the situation, because the water does not have any dissolved gas in it. To be precise, the gas can dissolve inside water, but it's very low. So the higher the water column, the more likely the operation of starting up well will fail. So this important piece of information can be derived from Olga as well. For example, one of the cases I worked on is did show there is more than 1,200 meters of water leg inside the well whenever the well shut in. But after 24 hours, this dropped to 300 meters. So Olga is very important to in determining these types of figures. And again, one of the main governing issues or main governing questions we use Olga to answer is during the shut-in and startup, how long is enough to shut in the well? For example, experiences usually show a well can start up between maybe 1 up to 3 days. If you shut in the well for more than 3 days, it starts, and the start is going to be better. However, in heavily fractured reservoirs, the pressure might migrate to other nearby wells. So the answer to this question is very complex, and there's no unique answer to populate on all the wells. So the best thing is to create an Olga model that can optimizes the best duration of the shutting for us. So what we are modeling, actually we are usually modeling the shutting periods. Is there any reinjection of the fluids happening inside the well? For example, gas, water, oil reinjection. We can usually match the static grading stations we already took in the field and match them against with Olga use cases or Olga results. We can match wellhead pressure, wellhead temperature, and we can determine the time required for our system to recharge in the near well bore, so we can open the well for production, and the production starts normally. For example, this is an example plot of the bottom hole pressure. So the well was producing up to hour almost 7, and after that, the shut-in procedure has commenced, and then we can see the pressure is after almost 33 hours of shutting, the pressure on the bottom wall is still rising. So this is an indication the recharge is not fully done. So you can just use Olga to find at which time it's possible for you to start the well again, so you don't over shut in your well. Another example is this plot. This plot is actually is a representation of water holdup with depth versus time. So the blue line in this is the status of water or the height of water in the well. So this is the x-axis is the depth, and the y-axis is the holdup. So the blue line is the well shut in after 2 hours. The orange line is after 10 hours, and the silver line is, or this gray line is the well shut in after 24 hours. So it's very pronounced. There is a regression in water height during shutting period. All of these can be answered using all the software. So that was for the shutting. And let's go to the startup. So what we are trying modeling in the startup, actually we are trying to optimize the valve size or the opening size of the valve. So we are maintaining as much pressure as much on the gas cap inside the well, so that gas does not escape all at once. We are trying to optimize as well the periods between the bin-ups or the periods between the choke size changes. We are trying to know what are the initial rates per phase during the startup and what are the stabilized rates. The startup, actually, we can monitor as well the buildups of the bottom hole pressure. Actually, the buildups is on the bottom hole pressure during simulation. This is not a good thing for us. This means there is no liquid, there is no efficient liquid unloading from the well. This is usually will cause the well to die in the upcoming days. We can schedule nitrogen lift using the simulator. We can optimize the nitrogen lift if the well did not start properly after using all the available methods to us. And we can maximize the anticipated produced hydrocarbon volumes at the surface. So we'll now go to the Olga software to take a look at the first case in the transient simulation. So I will launch my software. That can take a few minutes. So I'm using Olga 2017 version. This is the most reliable version I found on the internet. Other versions, they work. However, some modules, actually, they are missing from it. So if you are trying to use Olga or you are trying to start learning Olga 2017 version is the way to go. The software is somewhat on the heavier and the bloated side, so you need to be patient for a few minutes for the software to load up. So after the software has been loaded up properly, let me introduce you a little bit to the interface of the software. So it's evident to you what I am doing in the upcoming steps. So actually, Olga is old. We already said that a project was commenced in 1980s. However, the graphical user interface was later added to the software. So the software did not have any interface. The Olga is similar to Eclipse, meaning that it works on keywords. However, luckily for us, we don't need to deal with keywords since the graphical user interface generates the required code for us and adding components to the model. So few things that already exist in Olga. We have this right pane, this right panel. This is known as the model browser, meaning that whenever you are clicking on any component, you will get the properties for that. This is known as the model browser. On the left-hand side, we have the components that we can add to the system. You can see Olga has a lot of equipments or components we can add to the model. The nice thing about Olga is a single tool that can be used by many personnel. For example, I know people who are process engineers, they use Olga. I know people who are reservoir engineers that use Olga. People like myself who are production engineers, they use Olga as well. Production who are working on surface facility design or front-end engineering design, feed design, they can use Olga as well. So it's a tool for many peoples or many majors or many specialities. So what do we have here is we have a well. By the way, this well, you can just change the angle. This angle is just a cosmetic, so it's just for the looks. It does not mean it's changing the actual elevation or actual deviation in the well. So what we can do is this line, this is known as the well path or the flow path. If we double click on the line, so a panel will launch or another window will launch. This will show the well path for us. So this is our well path. So the well starts from here and it's end up in here. So the nice thing about Olga, you can divide your well or you can divide your any given flow path into as many as components as you like. And these components can vary in size and in thickness and in wall properties. And it can even vary in roughnesses. So this is a very nice addition from the Olga people. Additionally, the flow path should be placed between two nodes. The first node, usually the node that there is no flow exists from it. This is known as closed node. There is no information presented in the node, only the node name. After that node, you can add your source. For example, our inflow source or our fluid source is a reservoir. And then you have the node on the top side, which is known as the wellhead. This is known as a pressure node. So what's a pressure node inside Olga? Pressure node is a node that has a pressure specified. For example, we have this node that represents a wellhead. It has a pressure of 30 bar or something close to 420 psi gauge. It has a a temperature of 25 Celsius. So this is the wellhead node. You can add a valve. By the way, a valve, there's a universal component in Olga known as a valve. You can use valve as a packer. You can use it as a choke. You can use it as a regular gate valve. So there is a lot of use of valve inside of Olga. So you can say it's one of the core components you use inside the software. Upon clicking on valve, you can set the opening size of the valve and where the valve is located, and the internal diameter of the valve, and the discharge coefficient of the valve. So there is a lot of inputs you can manipulate with to match the performance of the valve. So without further diving in the properties of Olga, let's go ahead and run this model. So we click this, we run the model. By the way, this is a well model. So the simulation is finished. Usually the simulation takes time. However, it depends on the setup you are having in the well or the production system design. So the simulation actually is, I did the simulation for 9 hours. So now the simulation is now stopped. This is how we can write simulations in Olga. However, let's take a look what this well will behave during simulation. The behavior of the production system usually is controlled using a valve. So if you go click on the valve, and from the model browser, there is something called time series, this small nifty circle. If you click on it, it will show you the behavior of the valve with time. So it's showing me the behavior of the valve with the minutes. By the way, you can change it to hours or days or seconds. It depends on your preference. So from minute 0 to minute 60, the well is producing because the valve size is set to 1. So this is the relative opening. From minute 60 up to minute 360, so the valve is closed, meaning that the well is shut in this period, and then the valve is open up again. So the valve is the core components that lets you control your well or your production facility inside Olga. So we close this window and we can go ahead and see what the result was. And just a reminder, the simulation was run for 9 hours. How we can change the time for simulation or the duration of simulation, what we can do is we can go to case definitions. We can go to integration, and then we change the end time for the simulation. One cool thing about Olga is you can add a lot of files to Olga software. One of the main files we work with is PVT file. PVT file, it's different from other PVT files we're having in the oil and gas industry. This PVT file actually is specifically tailored for Olga software. I will show you how to generate these types of files. This is known as a tab file. I usually generate them using a software called Multiflash. This is a software by Kongsberg, and it was previously owned by KBC. The software is relatively easy to use, and it's not that complicated. If you know your way around the software, you can easily turn out a model in less than an hour. So this is the Multiflash software. This is usually used to generate tab files for Olga. What you can do, I'll just open up a ready file. So I don't want work on it. So it usually generates a phase behavior for us, and then we export the phase behavior as a tab file. So to export as a tab file, we go into this tab, and we go to export it as a tab file. And then it asks, do you want to export it for PipeSim or Prosper or Olga? So you can choose your model, and bam, you have your tab file. So this is how tab files can be generated for Olga. Multiflash software, actually, the Schlumberger guys have a contract with Multiflash guys. with the KPC or Kongsberg company, and they ship this software along with Olga, so you can do your fluid modeling with it. The cool thing about Olga is you can add multiple files, multiple fluid files, and the nice thing is you can assign a fluid file for each layer in the reservoir. That's, for me, that's very cool, because Olga will work out the mass balance between all of these files and turn out and generate a single fluid for us at the end of the node. So let's go ahead and view the results. To view the results inside Olga, we have three main ways to view the results. The first way is known as trend plot. The second way is the profile plot, and the third way is the 3D plot. We usually don't use 3D plots a lot. This is just a way of viewing data. However, we mainly rely on these two categories, which is the trend plot and the profile plot. So a trend plot is a plot in a single point. For example, we want to plot the wellhead pressure on this point. So this is known as a trend plot. If you want to plot the temperature and the pressure in the middle of the well, this is known as trend plot. However, the profile plot, it's different. It provides the same result for you. However, the result is provided along the path of the well. So this is something close to the static grading station. So let's take a look at the trend plot, and you will precisely know what I'm talking about. So we'll click on the trend plot. It shows the variables for us. By the way, the variable showing in here inside the Olga software, this is not all the variables that's presented in the Olga software. These variables should be explicitly selected by the user. Olga has something like more than 500 or 600 variables you can plot. So you cannot always select them all. You will select the variables you need. So let's arrange these variables by the location. So I will click on branch node position, and it will be arranged in that manner. So we have a position wellhead. The wellhead position has two variables, pressure and temperature. By the way, PT is the acronym for pressure inside Olga. This is a universal thing. And the temperature stands for temperature. You can change the units as well. So what I will do as an initial step is just plot the wellhead pressure. By the way, you can plot like 10 curves on the same chart. It does not matter. I will select the pressure and I will click OK. Now, this is the plot that it generated for me with time. So let's go ahead and plot another plot. Now, what I'm going to plot is I'm going to plot the bottom hole. So from the bottom hole position, what I can do is plot the pressure, and I will plot the oil rate with it. Oil rate in Olga is denoted as QOST, which stands for Q oil standard condition. So I will plot these two in the bottom hole position. I will click OK. So it will generate this plot for me. So for now, let me turn off the QO standard condition by clicking on the curve itself. Now it's much more precise what I am trying to do. Now what I am trying to do is I am presenting the pressure, the bottom hole pressure with time. So this is known as trend plot. From the bottom of the axis, I will change it to hours. So it's in the beginning of the simulation, I have the bottom hole pressure here is close something to 100,600. And only here, the shut-in start to occur, pressure started to build up. And for sure, there is no flow coming out of the well. However, we'll take a look at the Q oil curve for later. And in this period, you can see there is some pressure stabilization and other pressure hiccups. So those pressure hiccups can be um, gas pockets that's moving inside the well, or maybe some oil being injected or some influx happening inside the well. So this needs further investigation. Okay. And then in only in this position, which close to the hour 6, past the hour 6, the well starts flowing again by changing the valve size. If you or sorry, the valve opening. So the pressure dropped again. Now, whenever the pressure dropped, actually the well did not maintain the pressure drop. The pressure starts rising again. This is actually a bad sign, as we talked about it. This means that the well is being loaded with fluids and it's not coming out of the well. And here we are seeing some cyclic effects in the well. So let's go ahead and bring the oil rate with this plot. So the oil rate starts with the production of almost 400 barrels, and the production steadily declines. This is actually the production decline. This is a very signs there is something wrong with our production system. And whenever the well is closed, the production is close to zero. There's some instability in here. By the way, not all the instabilities inside oil gas is due to the flowing in the bottom hole. No, sometimes the instability happens during the numerical calculations. So up to here, the well was closed, and then the well was put online again. The well was producing 200 barrels whenever it was on the production, and then the production started to decline up to hour 8, where the production is almost zero. And then another cycle of production happened. The production jumps up to 500, and then it's close to zero. So this is a well that was shut in this period, a period from 1 hour up to 6 hours. So we shut in the well, and then we made it produce again, and the production is not very promising. Let's go ahead and change the simulation time. Let's see in 9 hours what will happen to the well. Let's set the simulation to 24 hours. Let's see how the well behaves. Okay, now the simulation is finished. Let's go ahead in the same plot and just click on the refresh. Whenever you are clicking on a refresh, this will automatically import the newly generated result for you. So in the previous simulation run, we almost simulated it for 9 hours. And in this simulation, we are continuing past the 9 hours. So it's very evident there is no production coming out of the well. If you hover on the oil rate, the oil rate is 5, and close to the end of the simulation, the oil rate is 3 barrels only. This can mean few things. The well, it can be interpreted as the well is not producing, or there is another explanation. Let's go ahead and plot the gas rate along with it, because what's happening inside the well is the heavier phase remains in the bottom, and the only gas will pass that phase and being produced in the surface. So this is known as the gas slippage. Let's go ahead and plot the gas with it. So we select a variable called QGST, which stands for gas flow rate at stock tank. It means the gas flow rate at these that standard conditions. So Um, Now, what we can see if we hover on it, both the oil rate and the gas rate, they are approaching zero, meaning that there is no flow is coming outside of the well. Although we know that the valve is open and the well should be producing. So now the turn off Olga software will come to solve this issue. This is known as the shutting and startup representation in Olga. So what we can do? Okay, let's go ahead back to our model. Maybe we're having issues on the back pressure. Let's just change or alleviate some of the back pressure. For example, the wellhead is 420 psi gauge. Let's just reduce the back pressure. For example, let's reduce it to 250 and rerun the model again. So you will try all of these scenarios inside Olga until you get a scenario where will you produce from the well without even being the need for the workover. We close the simulation. We will go to our plot and just refresh it. So I will just turn off the Q oil stock tank and just look at the pressure and the flow rate. So whenever I shut in the well, the rate is zero. After opening the well, the rate is almost 1200, and it's still increasing until hour 14. The well stabilizes, and the bottom hole pressure itself, it's stabilized. So meaning that the back pressure actually was making my well failure to start up. So that's a very, very important issue or very important factor we need to take into account. So this was the case for the shutting and the startup. Now I will close this project and we will go ahead and continue with the other slides. So in 2021, I published a paper on the SPE in the Decommissioning and Abandonment Symposium. The main idea of this paper is the first case we talked about, which is the shut-in and startup. And I also optimized the nitrogen lift from the well in the case of well did fail to produce. So this is a very recent paper, so you have to check it out if you are interested in shutting and startup scenarios using Olga. So before moving on to the second case, do anyone have a question about the case we took so far? Okay. So the second case we will talk about well cleanup. So what we are looking at here. So we have a well where it's loaded with drilling fluid or completion fluid, depends on your how you're looking at the issue or what type of well you're having. Are you receiving a well from completion or you're receiving a well after drilling? So it depends on the fluid you have. But whatever type of fluid you have, you can model it definitely in Olga. So the governing issues in this type of model is you have a heavy drilling mud inside the well. So whenever you have a drilling mud inside the well, this means that that mud was intentionally put inside the well to prevent the well from flowing. That's the purpose of heavy drilling mud. So under no circumstances you can displace this naturally, because this was intentionally made and there is some overbalanced density that's incorporated in this drilling mud value inside the well. So you cannot displace this mud naturally. And during the cleanup, usually there is no gas inside the well because the well is static, and you control the well using the primary well control method, which is the drilling mud. So what we are doing here, actually we are trying to optimize the nitrogen lift utilization. And as well, we are trying to displace the water-based mud and hopefully to start the producing from the well. So all of these are objects I can design using Olga and much many more. It's not just about to start a production. It's much important than starting a production is to maintain or sustain the production. This is very important topic. And definitely Olga can help you in that area. I will monitor the sustainability of the production. So meaning that I monitor the Q for all the phases, Q liquid and Q gas, Q water, Q oil. I will monitor the bottom hole pressure, wellhead pressure. Any buildup in the bottom hole pressure, we know it's a bad sign. And any decline in the wellhead pressure is after stabilization, this is a bad sign as well. So let's go ahead and launch the Olga software with this case. So this will take a few moments. So now the software is launched. Let's take a look at our model and what it contains. We can see there is the model browser we talked about, the right-hand panel. We have the left-hand panel, which is known as the components. And in the middle, we have our well. So the well has a bottom hole node. There is nothing in there, we already talked about, and there is a single producing zone. Let's go and take a look at the properties of this zone. So the pressure from that zone is 3,400. So this is the static pressure of the zone. Okay, so this is a P reservoir. And the temperature is 106. This is the temperature reservoir. Okay, and there is some locations that's assigned to that. Let's go take a look at the specifics of this inflow. We can find the parameters of the inflow in library, IPR, and usually inside Olga. The great thing is whenever you have reservoir inside Olga, you have to specify two types of inflow. The first one is going to be the production inflow, and the second one is going to be the injection inflow. Usually what people like myself do is we set both of them to the same value. However, this is it's not always the case in oil and gas fields. So it's very important to know if you have any injectivity information, you can add that inside Olga as well. So let's go ahead and click the production linear, which is the PEA productivity index. So let's change the units so we can see the productivity index is close to 50. We already talked about the transient behavior inside the IPR. What we can do is just click on this time series. And we can convert the time from second to maybe 2 days. And then I can specify, for example, at day 5, you can change the productivity index for, let's say, for 48. Maybe on the day 30, the productivity index going to be 37, 47, and so on and so forth. So I can manipulate these types of values. If you don't want to adjust the productivity index, you can adjust the reservoir pressure as well. So I'll just go ahead and delete those values because I don't want to manipulate the IPR results. You can decide this PI what phase it represents. Now I will go ahead and run the simulation. So this is known, the black screen is known as the command prompted. It shows you the results and the inputs into the Olga model. Till the model finish simulation, I'll take the chance to explain a few things that you might see here. So the input file is, let's say this is the generated file by the Olga. So this is the keyword files. Okay, so we actually we never ever open this and or work with it. This is something specific to the Olga internals. Okay, what we can see is all of these files that start with fluid, these are the tab files or the fluid files that's specified. From the looks of it, this model has 5 fluid different files. The first file is representing the properties of the production fluids or the hydrocarbon fluids. The second one is the nitrogen file, which will be used in nitrogen lift process in the simulation in the upcoming demonstration. And the other files, they are just mud files inside the Olga. So what we can do is just to view those files, we can go ahead to case definition, files, just click on this. We can see there are 5 files added to this project. You can add as many files as you like. So until the software runs simulation and finishes, the software will run for 10 hours. What this tool does inside Olga, this is known as a mass source. A mass source can be used for various of things. You can use it as an inlet for a pipe, or you can use it to inject nitrogen. You can use it to inject natural gas for gas lift. You can inject tracers, chemicals, whatever you like, you can inject with this mass source. So it's a very universal tool inside Olga. So let's take a look what's presented in this mass file, mass tool. We can go and see the time series. So we're injecting nitrogen for like 5 to 6 hours. And then the nitrogen injection is then stops. So I'll show it to you. So this is the mass injection for the nitrogen, which starts at minute 60, and then it ends at minutes 300. This is the period of the nitrogen injection. Well, what we are doing is we are trying to optimize this period of time, because there is no it's not justified to just not release the nitrogen unit whenever you are done with injection, because if the well is lifted and running for 5 or 6 hours of injection, you don't need to inject for 12 hours. So most of the time, this the value or the amount of injection time, this is not known for most companies. So they try to inject as long as possible until they get clean oil from the well or they sustain their production. But you can easily do this with Olga. So let's go ahead. So now 3 hours of results is showing. We can just go ahead and plot these without even waiting for the simulation to stop. What we can do is just go ahead and trend plot and just plot few variables. One of the things I missed to point out is this well contains mud inside it, inside the Olga model. So what we actually can monitor is the mud rates that's going outside of the model itself. So I will choose the mud rate, okay, and the pressure as well. You can monitor the pressure, and you can monitor the oil rate that's coming in outside from the well. I click OK. So it will start to generate this plot for me. So let's take it just curve by curve, because one of the ugly things about Olga plots, it can get messy very quickly. So I will turn off the oil rate and the pressure as well. So I will only focus on the mud rate. So from hour 0 up to hour 1, there is no mud coming out of the well. This is because there is no nitrogen injection that's presented inside the well. Let me just see if the variable of gas nitrogen injection is presented in here. Um, no, it's not presented. So what you can do is you can just plot the nitrogen injected rate in this area. But we already know this area does not have any injection. That's why there is no mud flowing out of the well. So after injection commenced, we can see some mud started coming out of the well. Okay. And then after 2 hours, there is no mud at all coming out of the well. Let's go and refresh this plot. So there's no mud coming out of it. So let me introduce the second variable, which is the oil rate. I will just click on it, so it will start to come out. So the oil rate is 0. Sometimes in Olga, you can see the rate as in minus. This means actually there is injection happening inside the well. This is usually if you have unbalanced pressure between the wellhead and the reservoir pressure. So all the pressures inside Olga should equal to the formation pressure. If the hydrostatic pressure is more than the formation pressure, you will have injection effect inside Olga until that balances out. So it's not a big deal. So once the injection is started, we can see the well start to produce some oil along with the mud. So until hour 2, it's not stable at all, and then it starts to stabilize. So the production starts to stabilize. Let me refresh the plot. Okay, now this is the production. No mud is coming out. So if you notice in the hour 5, there is some hiccup in the oil production. The oil production just got less. The reason for that is the nitrogen injection is stopped in that time. So one of the most important factors in Olga is to determine the stability of the production, when to stop injection, and how much to inject inside the Olga model. So let's go ahead and plot the pressure. So the pressure should be stabilized as well. You can see now let me turn off the mud curve. Now I'm plotting 2 curves, the pressure and the flow rate. So the pressure and the flow rate is very stabilized. So this is a good sign. Although simulation is not finished, we can see the straight line. So it's somewhat stabilized. Until there is, the simulation finishes, let's go ahead and travel back to the first period. I will turn off the oil rate plot and just focus on the pressure plot. So this is important for me. Okay, let me go ahead and try to plot the wellhead pressure with this as well. So I hope this is the wellhead pressure. Okay. Yeah. Now we are plotting both wellhead pressure and the bottom hole pressure. So the red line is the surface pressure, and the brown line is the bottom hole pressure. So let me just try to change the color of one of the curves so we can take a better look at. So the bottom hole pressure, I will just assign some color to it. Let's just assume it's purple or some distinctive color. Okay. So let's take a look at the initial cleanup period. We can see the bottom hole pressure when we commence injection. The bottom hole pressure is starting to rise. This is because I'm introducing a new phase in the well, and there is no flow from the top of the well. So this puts pressure on the formation or puts pressure on the well. So that's why we see some rise in pressure. However, whenever the mud starts to unload from the well, it's very evident. The bottom hole pressure starts to drop. So whenever I have a drop inside the well or in the bottom hole, it's very expected for me to have production because I am getting delta P. So this period is unstable period, and the cleanup is happening in this area. So until reaching our 2.5, the bottom hole pressure is 2,880. So the formation pressure is 3,400. We already know that value. So we have delta P, or we have a drawdown of something close to 600 psi. So in this plot, we are just seeing how the pressure in the surface and in the bottom hole is behaving. Let's go ahead and create another plot to see if the system is further stable. We will go to trend plot, and I will try to plot the oil rate, water rate, and gas rate, and gas oil ratio. So we will plot all these parameters. It's very necessary to plot as much parameter as you can to just ensure the system is up and running correctly. So I will zoom in this period. This is the initial cleanup period. We can see in the cleanup period, we are getting oil, gas, and water. And once the cleaning period finished, let's check out the production. We are producing oil. We're producing less than a barrel of water, so we can say zero water. And the GOR is something close to 500 static cubic feet per stock tank barrel. So all the parameters is very consistent. It's very necessary to note that usually when we are having an increase in production from Olga, an increase or a decrease, it's very necessary for the trends just to go up or go down all at the same time. For example, if I am having an increase in GOR inside the Olga model while I am having a decline in the oil rate, this is not a good sign, meaning that I am having a loading issue. Whenever I have a constant oil rate and increasing water cut, this is not a good sign as well, because the well might die, and I might have an issue with the production system on the actual life. So these are the values of information you can derive from Olga. If you go back to home, what we can do is I can assign an observation point in any depth I like, and I go about and do it like this. I go to positions, right click and add a position. This will be a monitoring position for me. So I will select the depth I like. Okay. I name the position. For example, I will name it mid well. And in the midwell, I will add any variable I would like. For example, I go to outputs, add trend data. So what we can do is just set the position or set the location for this. So I will add my midwell. And then in the general, I will just specify the variables. So I will show you the variables that Olga has. It's a lot. Actually, you cannot just navigate through the variables. Actually, what you can do is just search the variable name. For example, let's monitor the pressure in the position we added. So we will write PT or just write pressure. It will show the pressure for you. So we'll select PT. Let's go ahead and monitor the change in pressure or pressure derivative with time. We can write derivative. So it will show the pressure derivative for us. We can just monitor the temperature derivative as well. This is actually sometimes you can make use of these to know if there is any phase change inside the well. What I can do is just monitor the holdup, maybe monitor the liquid holdup, sorry, the water holdup only. So I will choose these and click OK. So for these results to show up, you all need to stop the simulation and run the simulation again. So this is very important. Otherwise, it will not work. Before we finish up this case, let me go ahead and show you the profile plot. So the profile plot is the plot with the depth. So that's what a profile plot is. One of the very nice tools inside Olga is the flow regime tool. So you see there is a variable here called ID. This is the flow regime identification. So the flow regime identification, it has only 4 values and they are all integers. If the curve shows 1, this means it's stratified flow. It shows 2, it means it's annular flow, 3 for slug, and 4 for bubble. So I will go ahead and select this, as well as I will plot the, let's say the holdup, the liquid holdup with it. So I will plot only these 2 values with depth. So when I click OK, it shows me a plot with depth. I will change the time from second to hour. The nice thing is this is a snapshot at a given time. For example, let's take a look. This is before even the simulation starts. We can see the well is filled up almost with liquid up to the surface. So we have only this period of time. There is no liquid in it. There is no liquid in it. So the well is pretty much filled. If you just move the slider, this shows the simulation results with time. For example, when I move the slider a little bit, now I am viewing the results for almost like 10 minutes or so. And it's showing me the holdup, the well is still filled with liquid. However, in this area, I am getting a punch and the holdup is decreasing. This usually happens in Olga for 2 reasons. Either you're injecting gas or you are getting gas from a formation. I'm sure I'm not getting gas from formation because this is the injection point I have. This is where I inject the gas. So if you go on with the simulation, you can see the flow regime, which is indicated as the black line, it's getting unstabilized. For example, in the bottom hole, which is where it's away from the gas injection, you can see the flow regime is stratified. This means that it's the flow regime is stratified and the flow is very slow. And it's filled with liquid. However, the regime changed to bubble close to the injection area. And from the injection area up to the surface, it's a bubble flow. So the flow regime identification is very, very important inside Olga, and it can use as well to identify the stabilities and instabilities in the system. So let's view the ending results at hour 10. This is our system. It's very important to know there is no gas in the system, no gas injection, no nitrogen injection. Here we have, this is known as the bubble point or the bubble point depth. In this point, gas starts to liberate from the oil. That's why the holdup starts to become less than 1. By the way, 1 holdup means 100% filled with liquid. HOL in Olga means liquid. Okay, so it means oil plus water. If you want to break up it further down between oil and water, so you need to plot those parameters as well to know how much percent of water you have. If we take a look at the black curve, which is known as the flow regime identification, we can see up to the depth of 1600 meters, we have stratified flow. Usually stratified flow in Olga means you have single phase, okay? Sorry. And then the flow is converted to annular. From the annular, now you have the number 4, which is bubble flow. You can plot other parameters as well, as much as you like. You can plot pressure with it. You can plot temperature. And you can view all the result as much as you like. So we'll go back to our slides. For the third and the final case, which is the crossflow. So what a crossflow is? Crossflow is the phenomenon of fluid exchange between 2 producing layers. So, for example, on the picture depicted on the right-hand side, we have 2 formations, formation A and formation B. There is a well that's penetrating to formation, and they are both I'm sorry, the mic got unplugged, so I plugged it back again. So what I was talking about is you have these 2 formations, formation A and formation B, and there is a well path that's penetrating these 2 formations. And those both formations are, they both perforated. So I am producing from these 2 formations at the same time. But what happens is usually one of the formation turns out to be like it has bad petrophysical properties, or maybe it's being depleted so fast, so faster than the other formation. What will happen is whenever I am producing from the formation B, if you have a depletion on formation A, you will have a fluid that's coming out from formation B and entering the formation A. This is known as a cross flow. This is usually detected using PLT or production logging tool. However, you can use Olga to model this as well. So let's take a look what we are dealing with. We usually are dealing with multiple reservoir models inside Olga, okay? And we are trying to figure out how much lost production we are having between intervals. So let's go ahead and have a quick look at the crossflow model. I will launch the Olga software. So I'm waiting for the model to launch. So we have this model in Olga where you have multiple producing zone. Those are depicted as well 1, well 2, and well 3. Well means just producing formation. It does not mean an actual well. No, it's just producing formation. If we run the simulation and go ahead and take a look at the results, let's go ahead and plot the oil rate and the gas rate. So this is the oil and the gas rate. So we can see both of them are just flat out. This means that either the model is not producing or we have some issue with the model. Let's go ahead and run the model. Let's go and plot the profile. We will plot the Q oil stock tank, Q gas stock tank. And if we plot the results, it's very evident there's some locations in the wellbore. They are contributing to production. Those are the humps. Those humps are the production. And there are some other locations inside the well. For example, this location, it's taking up a production. So this is the downward hump. So this is where the flow rates is negative. So meaning that the Olga model is it's producing from this location and it's being injected back in those two locations. This actually happens because of the difference in pressure between those two formations. So Olga will help us to decide whether we are having cross flow and the type of cross flow we are having and the degree of the fluid exchange between the reservoir, and whether we are having it in the flowing status or in the shutdown status. So this example was in the shutdown status. Let's go back to the slides and just continue with our presentation. So the next topic we'll talk about is using such a tool like Olga in production surveillance. We already saw what Olga can do, and now let's try to take leverage of it and just to automate the production modeling with it. So usually what companies do is they use Olga and connect it online. So they are connected to real data feed. For example, this is a dashboard that's created by a company called Paradigm. It was a part of Emerson. I think now it's part of Aspen Tech. What they are trying to do is they have this software called MET, and they are which software similar in category to Olga. What they are trying to do is they are connecting it to a real-time sensors and they are calculating result from it. So This gives you a great representation of the stability and instability you have inside such a system. If we take a look at the architect of connecting Olga or similar softwares online, which is something it's not hard to do. It only requires few skills you have. For example, the data starts from here, from number 1. So we have those various measurements or sensors in the field. They all have some identification number that going from the equipment to the PLC. And from the PLC, we can get them into the database. So we have some data flow coming from this side. What we can do is we store them inside SQL Server after cleaning up them and filtering them. And from the SQL Server, there is something another thing called OPC Server, which is a connection between Olga and any other software you like. So in this case, what we can do is just connect Olga to SQL Server and just exchange data with them. For example, in Olga, you have the wellhead pressure. You also the wellhead pressure and wellhead temperature. The issue with that is the wellhead pressure and wellhead temperature is just a single value. But what we can do is with OPC Server is you can change that value during runtime and as many times as you want. As a matter of fact, you can do it on real time. Whenever you are getting real time feed, you can just change the value inside Olga. So you will change the value inside Olga, you push the result in the Olga, and then Olga will push the results back to you. And whenever you get the results, now you have two options. Either you can inject it back in SQL Server, or you can just view it as a dashboard using programming languages like Python, C#, C++, or what any other languages you like. So you can do some virtual monitoring with these types of tools. Tools I know 100% you can do these things with it is LeaderFlow, Olga, Paradigm Meet, Petroleum Experts, 100% you can do that with it, and PipeSim. However, PipeSim and Petroleum Expert solutions, they usually are steady state solutions, not like Olga. So it's very different. So after knowing that, let's take a look at how we can automate production modeling using Olga. So this is a very important topic. Usually you will have multiple models. And what you want to do is to update those models whenever you have data coming from the database. So you don't need to open the model and update them and run them. What we can do is, let's assume we have, let's say 8 well models that's sitting inside a file system. What we can do is just write a code or script that opens up all those wells at the same time, extract all the information for us, and tabulate those informations. Nothing hard so far. Okay, what we can do is next is just to get the data from the database and update those models. When those models are updated, a user can review the update results and click on run. Whenever the model runs, you will get the results and you can view them in a dashboard, or you can export them in other oil and gas softwares. So this is known as the production model management or automated production model management. This can be applied to Olga, PipeSim, Prosper. All of these software, actually, they have some form of programming or scripting languages known as API, and you can use that and leverage it to manage our automated production modeling. Additionally, what you can do is just to link Office software packages with the dashboard or the data collection process. So you can use Excel for that and maybe generate some reports. One of the things we did back in 2014 is whenever we're having data coming in from the field using the sensors, for example, we set the models to 7 a.m. Each 7 a.m. the PipeSim models will run. It will collect the results and send the result into email into a predefined email list. So this is how we usually use the automated production modeling. So I'm very thankful for you for this opportunity and for listening. So I've been talking for almost 2 hours. Now it's your turn to ask questions.